morning, distinguished guests, ladies and gentlemen. In the few minutes, we're gonna start our opening ceremony. Could you please be seated inside the room? Thank you for your kind cooperation. Distinguished guests, ladies and gentlemen, in the few minutes, we're gonna start our opening ceremony. Could you please be seated in front of the stage? Thank you for your kind cooperation. Good morning, distinguished guests, ladies and gentlemen. In the few minutes, we're gonna start our opening ceremony. Could you please be
Thank you very much and kindly be seated.
Good morning, His Excellency, distinguished guests, ladies and gentlemen. First of all, I would like to introduce myself first. My name is Shutiman Chanthanivet. Very honored to be your MC for today.
Good morning, everyone. So I am Sanchai Kubun, a researcher from Nanotech. We are truly honored to be the master ceremony for the opening ceremony of the 9th Thailand International Conference on Nanotechnology, Nano Thailand 2025. This event organized by Nanotechnology Association of Thailand in collaboration with National Nanotechnology Center or Nanotech NASTA and the Research Network of Nanotechnology held from the 3rd to the 5th of November 2025 at this place Royal Orchid Sheraton Riverside Hotel, Bangkok, Thailand. The conference aims to stimulate the development of nanotechnology communities and to create a network of research and innovation among peers. Leading scientists, researchers from renowned institutes, universities, industries, and startups will come together to exchange advancement in nanoscience and nanotechnology and to explore opportunities for multidisciplinary cooperation. In addition, oral poster presentation as well as exhibitions and showcases from private sector will highlight innovative products and applications of nanotechnology.
Distinguished guests, this year's conference is held under the theme Revolutionizing the Futures, emphasizing the vital roles of nanotechnologies in creating life and better life and well-being for mankind.
Right. Ladies and gentlemen, to deliver the welcoming remarks, a brief of the conference, we are honored to invite the Executive Director and the Chair of Nanotech and the Chairperson of Nano Thailand 2025. Please give a round of applause to welcome Dr. Uracha Raktanonchai.
Your Excellency Dr. Phetdao Tomina, Vice Minister of Higher Education, Science, Research and Innovation. Your Excellencies, distinguished ambassadors and members of the diplomatic corps, honorable executives, respected guests, ladies and gentlemen. Good morning, สวัสดีค่ะ On behalf of the organizing committee, it is my great pleasure and privilege to welcome you all to Nano Thailand 2025, organizing under the theme, Revolutionizing the Future. Since its inception in 2008, 4 years after the establishment of the Nanotech Center, Nano Thailand has grown into international scientific conference for world-class nanotechnology that translate into tangible social and also economic values. As we gather for this time, the night, our mission remains clear: to transform excellent world class into science into the impact for Thailand and for the world. We are honored to welcome participants all over the world, from Asia, Europe, Americas, and beyond. So this year, the scientific sessions span across 12 sessions of 5 thematic tracks: health and biomedicine, energy and sustainability, food and agriculture, optoelectronics and manufacturing, and advanced tools and AI-driven discovery. Each track emphasized the pathway from discovery to industrial applications, highlighting the collaborations, ethical governance, real-world outcomes. Beyond the scientific sessions, we invite you all to explore our industrial exhibition over here that has been curated for business matchmaking and also youth-focused activities. This includes the high school project competitions, the 3-minute pitching awards, and the Young Nanotechnologist Award this year for the recognition. So these new initiatives are designed to inspire the innovator for tomorrow. We are so proud to inaugurate this year the Nanotechnology Hall of Fame. This is to honor individuals who dedicate an achievement through the advance both the nanotechnology and also national development. Our objectives are clear: to foster cross-sector collaborations, to accelerate commercializations, for advanced safety and regulatory frameworks, and to strengthen the pipelines from research to market-ready solutions. As the world continues to face many challenges, from climate change, health emergencies, food security, and digital transformation, nanotechnology stands out as one of powerful and cross-disciplinary enabling technology for sustainable solutions. Nano Thailand 2025 is not only a national showcase, but also international gateway for dialogue, for partnerships, and also knowledge exchange. So let us move forward, driven by curiosity, united by purpose, and committed to change and shape our sustainable and innovative future through nanotechnology. Thank you. ขอบคุณค่ะ
Thank you very much, Dr. Uracha Rakmanonchai, Executive Directors, Nanotech NASDA, and Chairpersons of Nano Thailand 2025 Organizing Committee.
Next would be really deeply honored for us to welcome Dr. Petdao Tomina, the Vice Minister of Higher Education, Science, Research and Innovations, to deliver the opening remarks and officially open the 9th Thailand International Conference on Nanotechnology, Nano Thailand 2025. Please kindly welcome the Vice Minister with a round of applause.
Your Excellency, Dato' Wan Zaidi Wan Abdullah, Ambassador of Malaysia, distinguished representative of the embassies of the People's Republic of China, France, Japan, and Vietnam, honor leaders from government, academia, and industry, esteemed guests, colleagues, and friends. Good morning, สวัสดีค่ะ It's a profound honor and privilege to welcome you all to Nano Thailand 2025. This gathering is far more than a scientific conference. It stands a forum of vision, a celebration of progress, and above all, a powerful testament to the enduring strength of partnership. Under the theme, Revolutionizing the Future, we reaffirm our shared commitment, both national and global, to transform knowledge at the smallest scale into innovations of the greatest consequence. Though nanotechnology operates within the invisible realm, its impact is anything but unseen. It reshapes industries, enhances human well-being, empowers emerging economies, and redefines the very foundation upon which our shared future will be built. Since its establishment in 2008, Nano Thailand has grown into a beacon of scientific ambition and collaborative spirit. It has become a space where ideas are exchanged, insights accelerate, and partnerships flourish, transcending disciplines, sectors, and national boundaries alike. Yet, let us recognize this truth. No nation can single-handedly unlock the full promise of nanotechnology. Progress at the nanoscale demands cooperation at the global scale, whether in the pursuit of sustainable energy, advanced materials, precision medicine, or next-generation manufacturing. International collaboration accelerates discovery, strengthens standards, and builds resilience for all. Your presence here today, representing government, academia, industry, and next generation of innovators, reflects that very spirit of shared purpose. Each of you carries a vital piece of the global solution. Over the coming 3 days, may we align our respective strengths, transforming blueprints into breakthroughs and ambition into collective action. To our scientists and students, your curiosity and dedication are the lifeblood of discovery. To our policymakers, your vision and foresight create the frameworks within which innovation thrives. To our industry partners, your courage to adopt, adapt, and advance turns research into real-world impact. And to our international delegates, your trust and collaboration breathe life into global progress. Nano Thailand 2025 is not merely a stage. It is a launch pad for the future. May it ignite enduring alliance, transform ideas into enterprises, and reaffirm our shared pledge to ensure that science continues to serve humanity and society. As we embark on this day of dialogue and discovery, let us, guided by 3 enduring principles. Let us discover with discipline, for true progress is born with rigorous understanding. Let us translate with purpose, for innovation attains meaning only when it uplifts life. And let us scale with integrity, ensuring that safety, sustainability, and ethics remain at the heart of every step we take. Together, let us not only revolutionize the future, but shape one that equitable, inclusive, and enduring. Thank you, and may Nano Thailand 2025 stand as a conference of inspiration, collaboration, and global resonance. Thank you very much. ขอบคุณค่ะ
Thank you very much, Dr. Pekka Bopina, Prime Minister for Higher Education, Science Research and Innovation. Could you please kindly remain on the stage to join the next photo group section on the stage, please?
As we can see that this is the 9th conference of Nano Thailand 2025. So it represents that Nano Thailand has been growing up. So thank you everyone for being with us from the beginning. And now for those who just come for the first time, so you are really welcoming to make this community grow up.
All right, up next, you're going to have our group section together. And first, I would like to invite Professor we will open the floor for you. You can raise your hands or maybe you can take a note on the papers while our speakers speak on the stage. In the N&D section, you can ask for more questions. Please feel free to ask the question to our speaker as well.
That's correct. So we will try to make this event become as interactive as much as possible. So please ensure to engage and to ask any questions you may have. This is really good opportunities to be able to meet with the renowned scientists in nanotechnology. So hopefully we're going to have really good exchange during this period.
Alright, so the next section we're gonna take about 40 minutes, and so after that we will have coffee break for you, and you can have the chance to go to visit our exhibition over there beside on the stage that you can get for more information about nanotechnologies and get for more information about our sponsor who come to support this event or organizing this event as well.
That's correct. And today after the first talk, and we're gonna have you have some time on that one, so you're going to be able to explore the event. And I think the first talk is ready already. So next, I would like to invite the very first plenary speaker. So he's going to present in the topic of nanostructure catalyst for sustainable energy and environmental uses by Professor Hiromi Yamashita. At this moment, I'd like to welcome Professor Mehta Charan-Panit, the chairperson in Green Catalysis for Sustainable Consumption and Production, to give some brief introduction about our plenary speaker. Please give a round of applause to welcome Professor Mehta.
Your Excellency, Dr. Pret Dao Tok Mina, Vice Ministry for Higher Education, Science, Research and Innovations, Dato' Wan Saidiwan Abdullah, Ambassador of Malaysia, distinguished representative from Embassy of Canada, People's Republics of China, France, Japan, and Vietnam, honor executive from government and private sector, distinguished guests, ladies and gentlemen. Welcome to the Nano Thailand 2025 conference, Revolutionizing the Future. Well, first of all, let me introduce our plenary speakers, Professor Hiromi Yamashita. Professor Yamashita worked at University of Osaka since 2004. He earned his PhD from Kyoto University in 1987. He served as assistant professor at Tohoku University, an associate professor at Osaka Prefecture University, and invited professor at the University of Pierre Marie Curie. He has been an editor of Applied Catalysis B, a member of Academia Europaea, and served as the president of the Asia Pacific Association of Catalysis Societies from 2019 to 2023, as well as the president of the Catalyst Societies of Japan from 2019 to 2020. Professor Yamashita has received numerous awards from organizations including Asia Pacific Association of Catalyst Societies, International Mesostructure Materials Associations, Chemical Societies of Japan, Catalysis Societies of Japan, Japanese Photochemistry Association, Japan Petroleum Institute, and Japan Institute of Metal and Materials, and many others. Today, he will speak on the science of nanostructure catalysts for sustainable energy and environmental use. Ladies and gentlemen, please join me in welcoming Professor Yamashita.
Professor Mehta, thank you very much for kind introduction. Good morning. I'm Hiromi Yamashita, coming from Osaka University, Japan. At first, I want to appreciate the chair and organizing committee member of Nanotech conference, also Nanotech Association. It's my great honor to speak here. Actually, my nephew is working in the Bangkok, and my first student became a professor. Mehta is a professor of Kasetsart University. Bangkok, Thailand is very close to me and my family. Thank you very much. So today's topic is the design of nanostructure catalyst for energy and environmental use. Actually, I make some brief introduction, but already Professor Mehta introduced. But sorry. I graduated Kyoto University, and my department produced the 3 Nobel Prize winners. This year, Professor Kitaga get the award, and I heard he make a lecture 2 years ago. So it's my great honor to speak here. And I started the career in Tohoku University, and Professor Mehta is my first student. So I'm very honored to speak. I skip this one because she already introduced. I want to little bit introduce Osaka University. Now name changed to the University of Osaka. It's located in the middle of Japan and very close to the old capital Japan, Kyoto. So you can, if you come to Osaka and Kyoto, you can enjoy the many world heritage, Himeji Castle and Golden Temple. Also, very delicious Japanese food, sushi tempura. Please come to Osaka. And my campus is located in northern part of Osaka. And recently, we have an expo in Bay Area, but it's finished last month. There is a Thailand pavilion. It's a very popular, many persons to try to enter. So we are happy to successful expo. And I want to start my talk. I will talk the nanostructure catalyst. This is an example of metal nanocatalyst. They are very useful for energy, environmental, green chemistry. Sometimes we use a porous bulk metal, but most cases we use a metal support system. If we can control the interaction of metal and support, we can design the size and the morphology and the surface component of nanoparticles. For example, single metal cluster, nanoparticle, single metal alloy, solid solution, intermetallic compound, core shell alloy, and high entropy alloy. They are very useful for many applications. We must consider to design the nanocatalyst, we must consider the fundamental theory of catalyst. For solid catalyst, adsorption step is a very important step, and adsorption occurs at special surface site. Also, interaction on the surface and the reagent is very important. Moderate interaction is very good for the efficient catalytic reaction. So we must, to design the nanocatalyst, we must consider the design of active site and reaction field. To design the nanostructure catalyst, we must consider 3 key points. Design of active site, design of reaction field, and design of energy injection. On active site, we must consider number, coordination, and electronic state and ensemble. For design of reaction field, it's very important to realize the efficient catalyst. We must consider space and morphology, size and morphology, and the surface chemical properties, such as hydrophilic, hydrophobic, acid-basic properties. Also, energy injection to the active site, very important. We use heat for thermal catalyst and light for photocatalyst and electron for electron catalyst. So this is the image of design of nanocatalyst. Not only the active site, design of reaction field to enhance the reagent is very important. So we try to synthesize the hybrid material for porous support and active photocatalyst and nanocatalyst to design the new chemical processes. To the support, nanoporous material very useful because they have a nanostructure, so they can have a large surface area, high dispersion of active site, and condensation of reagent. And many cases, framework is transparent to light. So we can use such a cavity as a molecular reactor for efficient catalysis for energy, environmental, and green chemistry. As a candidate of nanoporous material, we can use a microporous zeolite, mesoporous silica, macroporous silica, core shell, yolk shell, and MOF is also one good candidate. And I'm happy to inform Professor Kitaga get a Nobel Award on these topics. And we can use the interlayer material, porous carbon polymer, and the top surface of thin film. We can combine such a reaction field with the active site using the semiconductor metal complex, single site catalyst, also nanoparticle and plasmonic nanoparticles. Today, I want to introduce the hybrid with the nanoporous material and photocatalyst and nanocatalyst. I will talk on these topics: semiconductor, single site, plasmonic nanoparticle, MOF, yolk shell structures. First topic is semiconductor TiO2 application. So TiO2 semiconductor is a very famous for application for artificial photosynthesis to produce the hydrogen and reduction of CO2. But practical application, they use the degradation property and superhydrophilic property, so they can keep self-cleaning and anti-fogging properties. Many applications already made using such properties. In the case of degradation of organic pollutant reduced in air and water, combination of porous support and photocatalyst is very important to realize efficient adsorption condensation. Hybrid with porous support is very important to enhance the photocatalytic reactions. So we can design the hybrid with photocatalyst and porous material. If we use a cavity and the top surface, we can synthesize a small particle of semiconductor, and they are very good at complete degradation. If we make anchoring in the metal site into the framework, we can synthesize the isolated active species, and they show the unique activity, so we call such active site as a single site photocatalyst. So they show the very unique properties. This is an example of degradation of organics diluting water. In this case, we use a hybrid of TiO2 photocatalyst and zeolite materials. So by changing the zeolite support, by changing the silica-alumina ratio, good photocatalytic degradation observed this area, and this material is small water adsorption. So it means a hybrid with hydrophobic surface is efficient for photocatalytic degradation. But most cases, nanoporous material inside surface chemistry is hydrophilic, because we must remove the template to produce the microstructure. So inside the surface have some damage and to show the hydrophilic properties. So we must make a surface modification of inside the cavity by using organics, fluorine, graphene, apartate polymers. So after modification, inside surface became a hydrophobic property to realize the efficient adsorption of organic reagent. This is an example of fluorine coating of zeolite. After fluorine coating, surface water adsorption property decreases. It means the surface changes to hydrophobic properties. With the increased fluorine coating amount, they show the higher photocatalytic degradation. Finally, they show the higher activity than the commercial semiconductor photocatalyst. But not only the surface chemical property, also size and morphology of porous support is very important. We can use a microporous zeolite, mesoporous silica, and macroporous silica. Using this procedure, using the colloidal crystal void space, we can synthesize mesoporous structure, and after calcination of polymer, we can design the three-dimensional porous structure with the mesopore and macropores. Such a support is very good at photocatalyst enhancement. In the case of small molecule degradation, there is not a big difference with and without macropore. But in the case of degradation, large molecule enhancement of activity can be observed on using the macropore support. So efficient diffusion of reagent can be realized efficient photocatalytic degradation with macro mesostructures. Next topic is a single site photocatalyst application. As mentioned, we can synthesize a single metal photocatalyst using the bimetal implantation into the framework. We can synthesize a single site catalyst using titanium, vanadium, chrome, molybdenum, tungstens. We also can use a cavity for designing the photofunctional metal complex. They also consider the single site photocatalyst showing the unique properties. So this is an example of CO2 reduction using the single site photocatalyst. Compared with the semiconductor type, they show the larger activity, and also they show the not only methane and methanol. And this activity and selectivity much depend on the pore size and morphologies. So size and structure and surface hydrophobic property of support is very important to control the single site photocatalyst. So we can also design the photofunctional metal complex using the nano cavities, and they show the very unique photocatalytic activities. For example, this is the ion complex. Pure ion complex, almost no adsorption at the visible light region, but after anchoring into the nano cavity, they started to show the adsorption at visible light because of ligand distortion. If we excite such a band, we can realize the efficient photocatalyst with high selectivity to produce partial oxidation, epoxide. So mesopore support is more useful to design the metal complex single site photocatalyst. By control the concentration of metal complex, we can design the dimer active site. They work as an efficient photosensitizer and hydrogen production catalyst. So depending on the porous structure support, hydrogen production can be controlled. In this case, three-dimensional porous mesoporous silica is a good support for hydrogen production. Next topic is the application of plasmonic nanoparticles. Light irradiation of noble metal nanoparticles such as silver and gold, surface electron density can be modified. Such a phenomenon can be called as a localized surface plasmonic resources. Using this excitation, we can control the surface electron density. So such a change of surface electron density can enhance the catalytic performance. To control the plasmonic effect, we must select the metal source, and we must design the shape of nanoparticle, also size of nanoparticle. If we succeed such a design of nanostructure, we can synthesize the nanometal particle showing the various colors. So it means that we can use various light source for photocatalytic reaction. we try to use such a plasmonic catalyst for hydrogen storage as transportation system. Using the renewable solar energy, we can synthesize the hydrogen in the countryside. But to use the hydrogen in the city by fuel cell, we must make a transportation of hydrogen. For this purpose, some hydrogen carrier molecules such as ammonia, boron, ammonia, and formic acid is very attractive because they have a large amount of hydrogen in the molecule and they can reduce the hydrogen by the catalyst reaction at low temperatures. So we apply the plasmonic catalyst for this purpose. So we make silver nanoparticle using the metal cavities by using the uniform rapid heating of microwave heating. So we can control the size and morphology of nanoparticle in the cavity. So this is the result of preparation of nano silver metal. If we use a stabilizer, we can control the size of nanoparticle and they show the yellow color. Without ligand, lot type of silver metal can be synthesized. They show the red color and control the preparation condition. We can make a lot type with a large aspect ratio. They show the blue color. So we can control the metal, we can synthesize metal nanoparticle with various colors. So we tried this reaction produce the hydrogen from ammonia boron, and light irradiation enhancement of activity can be realized by the plasmonic effect of silver nanoparticle, especially rod type with large aspect ratio, so the efficient enhancement by the plasmonic effect. We can hybrid with palladium as a catalyst, so large enhancement of hydrogen production can be realized with such a hybrid palladium catalyst and silver plasmonic nanoparticles. But silver gold is very expensive, so if we can synthesize a nanoparticle using the earth abundant cheap material, it's very convenient. So for this purpose, we use a molybdenum oxide to synthesize the plasmonic, showing the dark blue colors. This is a hydrogen dope nano sheet. They show the blue colors by the plasmonic effect. We carried out hydrogen production. Even dark condition, hydrogen dope molybdenum shows a higher activity. And under visible light radiation, large enhancement of activity can be realized by the plasmonic effect. So activation of plasmonic band is very important. From characterization, we can see that such a hydrogen dope molybdenum oxide have a reduced molybdenum 5 plus, also large amount of surface oxygen defect size. Such a defect oxygen site works as a CO2 reduction site to produce carbon monoxide. Also, this site can be activated by the plasmonic effect, so we can realize the efficient CO2 reduction to produce carbon monoxide. So this is the result of CO2 reduction produce carbon monoxide. Hydrogen dope molybdenum oxide shows a large activity, and under light irradiation, good response can be observed, and the enhancement of activity can be realized by the hydrogen photo irradiation. Large enhancement to produce carbon monoxide can be realized. So formic acid is another candidate of hydrogen carrier. Also, if we can recover the CO2 to produce formic acid again, we can realize the hydrogen transfer, also recycle of carbon. So for this purpose, we designed the palladium-based alloy nano metal alloy catalyst. This is an example of palladium catalyst supported on the polymer resins. we can control the acidity or basicity of surface by changing the functional groups. This bar shows the hydrogen production on the palladium catalyst. So hybrid with support with weak basic site is very efficient for hydrogen production. From the theoretical calculation, we can find a weak basic site to enhance the dissociation of OH bond, so we can produce hydrogen efficiently from formic acid. Surface electron state of palladium is also very important. By making an alloy with silver, surface of palladium became electron rich. Such an electron-rich palladium protects the strong CO adsorption and accept the formic acid efficiently. So silver alloy catalyst shows a higher activity than the pure palladium. So next topic is the MOF. Already you know the Professor Kitaga get an award on MOF. And MOF can be synthesized from metal oxide and organic ligand. So such using various sources, we can synthesize various type of MOF structures. MOF is a very good candidate for catalyst and support because they have a porous structure and large surface area. We can realize a high dispersion of active site and realize a high efficient condensation of reactant. We can also make a modification of surface chemical properties such as acid-basic and hydrophilic and hydrophobic property. Also, such a ligand and metal cluster show the unique activation as a unique charge separation as a attractive photocatalyst. So MOF is a good candidate of photocatalyst material. I try to use a MOF catalyst to realize the artificial photosynthesis. In this case, we make a reduction of molecular oxygen to produce hydrogen peroxide. Hydrogen peroxide can use a fuel for the fuel cell. So this hydrogen peroxide considered as one of solar fuels. So we try to synthesize the hydrogen peroxide using the MOF photocatalyst. Already I make several research, effect of nanoparticle addition and effect of ligand modification and effect of cluster modification and the effect of reaction system using the two-phase reaction system. This is one of the example. If we make addition of missing linker site in the framework, they show the larger activity for hydrogen peroxide. Because they, with the missing linker site, efficient charge separation occur and the surface change to hydrophilic, from hydrophilic to hydrophobic. So hydrophobic surface can protect the decomposition of hydrogen peroxide. So we can produce a large amount of hydrogen peroxide with MOF having a missing linker site. But if we carried out a reaction using the one-phase reaction, produced hydrogen peroxide can easily contact with the catalyst and they easily decompose. So to escape the direct contact with hydrogen peroxide and catalyst, we use a two-phase system using the aqueous solution and organic solution. Using two-phase system, we can separate the produced hydrogen peroxide and catalyst, so we can protect the decomposition of hydrogen peroxide. But originally, MOF is hydrophilic because of amino functional group, so we must modify by the alkylation with this process, and finally, surface became from hydrophilic to hydrophobic. So modified morph scattered in the organic phase. This is the original morph and located in the aqueous solution. After modification, they located in the organic solution. And by the modification of alkylation, production of hydroperoxide can be enhanced. Also, using this reagent, we can make a change of hydrophobic property only covering the top surface of porous structure. So we can succeed to keep a large porous structure, a large surface area of porous structure. So in this case, more enhancement of produced hydrogen peroxide can be realized. So final topic is the yolk shell structure application for CO2 captures. Yolk shell structure is very unique. Using this cavity, we can design the various hybrid materials. In this case, we hybrid with aminopolymer for CO2 adsorption and alloy catalyst for CO2 reduction. So such a hybrid material realize the efficient CO2 conversion to formic acid. This is the result. Without the shell structure, without a polymer, they show a small activity. But the hybrid with polymer and alloy catalyst system in the core shell structure, large enhancement of production of formic acid from CO2 can be realized. We can design the shell structure using the carbon. If we hybrid catalyst with polymer, enhancement of activity of CO2 reduction to produce carbon monoxide and produce hydrogen from water can be realized efficiently at the moderate amount of polymers. So without polymer, only hydrogen from water can be produced, but to hybrid with polymer, we can produce the hydrogen and carbon monoxide as a syngas source. So carbon shell is also very useful for electron catalyst materials. So our purpose to realize efficient CO2 conversion and recycling, we designed the adsorbent such as aminopolymer, also calcium compound. We hybrid such adsorbent and efficient catalyst for plasma catalyst and metal complex and alloy catalyst. Such a hybrid material can produce efficient CO2 conversion and carbon recycling. This is a member of our group last year, and this association support our research. And we have a talk at conference in next year, so please come to Tokyo again, Japan. Thank you for attention.
Round of applause for Professor Yamashita. A very interesting talk. So may I briefly summarize about the talk? So basically he mentioned something about nanocatalysts. So really interesting idea that by having the porous materials together with the metal active sites, so looking at the key points to design the catalyst by looking at the active sites, reaction fields, and also the energy source using for that particular reactions, and then can design. So there are many different kind of porous materials and different metals that can be used for the catalyst for particular reactions. So by doing so, he discovered a lot of interesting idea about using the nanoporous materials as the molecular reactor. So if we imagine reactor usually big, but this one is really cool idea. So thank you very much. At this moment, we would like to.
All right, so could you please remain on the stage? We're going to go to Q&A section. And next, I would like to welcome back Professor Mehta Chalerm Pradit, the chairperson in Greens, characterizes for sustainable consumptions and productions. Go to Q&A section. Big loud applause to welcome her, please.
Thank you again for your very nice and interesting talk. So we will have about 10 minutes for the question from the floor.
All right, if anyone have the question, you can raise your hands. Our staff will bring the microphone to you.
I can start first.
Yeah,
Yeah,
we really need
okay.
the
For
first
the first
person.
questions, please.
Okay. Actually, we do curious about the future of photocatalysis and also the catalyst that will be very active for a kind of carbon capture utilization in the future. Do you have any idea to inform or exchange with us?
Maybe photocatalysis in future, very new material will be appear to realize efficient conversion. But design of reactor, how to make a photoirradiation, it's very difficult for practical application. And for carbon recycling, the hydrogen recycling, I think nanoparticle, metal particle is a very, very hopeful. So maybe future we can successful to design the hydrogen recycling using the hydrogen carrier molecule, also CO2 reduction. Yeah.
Yeah,
I
thank
think
you
we
very
feel-
much.
yes.
Yeah. Any other questions?
Do you have one more question from the floor? Yeah, please,
Over
over
there.
there.
Okay.
Thank you very much, Professor, for your excellent talk, and that give us a very great idea of how we can use the particle for energy and sustainability. From your presentation, we can see that there will be more and more use of nanomaterial in the people life. So, what could you give a comment or remark on regarding nano safety in terms of use of nanomaterial?
So for design of nanocatalysts, many researchers concentrate on design of active site. But more important is the design of reaction field. Reaction field design is very important to enhance the absorption of reagent and efficient diffusions. So not only the active site, we must consider reaction field. Of course, some nanomaterial sometimes dangerous, so we must select the stable material and safe material, of course. Thank you for attention.
Thank you very much.
Okay, so if there is no more question, I am not sure if there is still one last question if you really want to ask. And I think we can continue ask questions later, I think. Okay, at this moment, thank you, Professor
Thank you
Mehta, very much.
Thank you.
And also, we're going to have the photo session. And I think you have something in your hand right now.
Yeah.
So what is that?
Let's see if we have a mouth in our hand. This is the products of Nanotechnology Center. So this will be, we can have a kind of the contracts of our future for the collaborations. Okay, thank you very much.
Right.
Moment.
So we're going to have the picture to prove that research and innovation in nanotechnology. We're starting from fundamental and some applications to improve daily life, enhance industry competitiveness, and support sustainable future. So there's gonna be a lot for you to explore.
Yeah, so it's time to explore together at our exhibition over there beside the stage, and we're also preparing all coffee bag for you as well that you can feel your energies. And we would love to inform you that in this afternoon around 1 p.m. we will have another section that's very interesting about nanotechnologies. So please come back to join with us.
Right, so please come back to this hall at 1 p.m. for more interesting talks. So at this moment, enjoy your break and enjoy learning and sharing some experience in nanotechnology. Thank you everyone very much for your kind participation. ขอบคุณครับ